the simple proof and delved into the nuances of the triangle's area formula. Today we set the stage for one of math's most celebrated proofs, Euclid's proof from the elements, proposition 1.47. And this proof isn't just a part of math history. It resembles a masterpiece for its profound impact on human thought. Like it bridges the gap between the Odyssey and the Mona Lisa. Imagine stepping back 2,000 years and adopting the Greek perspective where algebra was not the tool. No, it's all about geometry. In our scenario, our familiar 3-4-5 triangle is not just lines on paper. It represents land, with each square unit a mile. Imagine a farmer named Leo who diligently plants beans in his smallest field, a 3-by-3 mile square, or 9 square miles, and corn in the next field, 4-by-4, or 16 square miles. His largest field, 5-by-5, covers 25 square miles, equal to 16,000 acres, matching the sum total acreage of the smaller fields. Leo's decision on how to plant his field is not just practical, it's profoundly geometrical. He opts to divide his largest field to mirror the proportions of his crops' smaller fields, 5,760 acres of beans and 10,240 acres of corn. Now, he has many geometrical options, such as 3-by-3 beans and the rest corn, or 4-by-4 corn and the rest beans. His method is a simple but brilliant rectangle. Now, if Leo was a modern farmer, he could use algebra to decide where to divide that field that creates perfect symmetry and balance. But Leo consults with Euclid, and Euclid uses the land as a canvas to illustrate the deeper connections within the triangle. He drew 3 lines, not in the sand, but across fields, turning agricultural practices into a live demonstration of geometric principles. These lines are not just divisions. They are the keys to unlocking the proof. Euclid's first stroke of genius was a line perpendicular to the hypotenuse from point P through square C. And this move wasn't just about splitting land, it was about illustrating the inherent symmetry in right triangles. Notice this is the same perpendicular that we drew in the first proof, but it now extends outside the triangle. To complete the proof, we must show the beans planted in the rectangle, C, matches the area of the beans planted in square B, and then we repeat the process for corn. Euclid's second genius stroke was drawing a segment from C to E, creating triangle red, and his third move was similar, drawing a segment from B to F, creating triangle blue. And if you compare these triangles, you'll notice that they are congruent by Euclid's own side-angle-side theorem, or SAS. Now, this caught me by surprise, so let's plow into the details. We get the sides equal because they are sides of squares. For the angles, consider the red and blue angles centered at point A. And notice angle CAB is part of both triangles, red and blue, and the only thing that we're missing are 2 right angles. And we know right angles equate, and angle CAB is congruent to itself, then we can conclude that the red and blue angles at point A are congruent, because both angles measure 90 plus x, where x is the angle measurement for CAB. And thus, the triangles are congruent, meaning they have equal area, and we have the pleasure of visualizing this simply by rotating triangle blue until it becomes a triangle eclipse with triangle red. We can see this proof in all the relationships and symmetries at play as we change the size of our right triangle. This is interesting, but how do all these moves help us prove the theorem? The master geometer does not waste moves, and now we see Euclid's genius in full bloom by comparing triangle blue to square green. We created the previous video about area to prepare us for the big moment, and the big moment is now. Notice the triangle and square share the same side AF. So if segment AF is the triangle's base, then what is the triangle's height? Recall, height equals the perpendicular segment from the base until it meets the parallel line that intersects the top of the triangle, which means height is segment AC, since AC is perpendicular to AF and GB. The shocker is our square has the same base, the black line, and same height, red line, as the triangle. A square, of course, is a special case for a rectangle. And this all leads to the wonderful conclusion that the area of the blue triangle is 1/2 times the area of the green square. Now, simply rinse and repeat for triangle red and rectangle green. Both share the same base AE and height AP. Therefore, the area of the triangle is half the area of the rectangle. And since the blue and red triangles are congruent, and the area for each triangle is 1/2 the area for the square or rectangle, then the area of the green square and green rectangle must equate. We have arrived at proving the square bean field has the same area as the rectangular bean field. Then simply replace beans with corn, switch labels B and A, and retell the same story for the other square, which completes Euclid's proof that A squared plus B squared always equals C squared. This isn't just theory, it's the reality of the land measured in acres of crops. Isn't it amazing that we're proving the formula that calculates the distance between the points of a right triangle, and our proof involves areas, such as square miles or acres? In math, we jump from one dimension to another and act as if nothing weird just happened. But this is all very strange stuff. Digesting and understanding Euclid's proof requires extra effort. Realize, though, we just went inside the mind of one of the greatest math persons of all time. And this is one of his greatest achievements, which I'll add has been revered by many smart people after him. And now, this triumph of thought is simmering inside your mind. We have one more masterpiece of the mind to navigate. But first, we will uncover one more composition involving the area of a triangle to prepare us for the weeds ahead. Remain curious.